Okay, in the previous video, I talked about evaluating log expressions and solving log equations. In that video, I did two fairly simple examples of solving logarithmic equations. In this video, I wanted to take the time to do just a couple of examples that were a little bit more challenging. And if you remember, when we are solving log equations, there's really a process to follow. Number one, we need to make sure that it is a log equation. And so typically you're going to see the word log in there. In fact, maybe more than once. And then that variable that you're trying to solve for, it's going to be embedded in at least one of those logs. Maybe more than one, as we'll see in this next example. So number one, is it a log equation? Number two, once you recognize it's a log equation, which process should you use to solve it? Should we be using the one-to-one process, or should we use the inverse property? Again, the one-to-one is usually the fastest way to go solve those. If the problem is one-to-one, they are not all one-to-one, which means we would need to do the inverse property instead, which says we're going to take that log and turn it into its inverse function, turn it into the exponential instead. And then finally, most importantly, is don't forget to check your answers. Because that variable we're looking for is in the argument of a log, there could be some domain restrictions there. And we need to make sure that algebraically, any answers that we get are actually legal, that they're allowed, that they're part of the domain. In fact, when I did those brief examples in the previous video, here down below, I had done an example of a one-to-one property and an example of an inverse property. And I realized after I posted the video that I had forgotten, shame on me, to actually check the answer that we had gotten. And so the answer was allowed. It did work. When we had solved this log equation, we had gotten this as our exact answer, which as a decimal is just over 19. And clearly, if you take that value as your answer and stick it back up into this argument, this entire expression has to be positive. And if you take a number that's slightly above 19 and add 1 to it, that's definitely going to be a positive value, so we're okay. So again, can't stress enough the importance of checking your answers when you're done. Okay, so I have three examples I'm going to do, and let's get started. So this problem right here, definitely a log, because the variable I'm trying to find, the x, not only is it embedded in one log, we see it's actually embedded in several logs. So then the next question is it one-to-one? This does not look like it's one-to-one initially, because we don't have a log equals a log. I have more than two logs. So, but we need to ask ourselves, can I make it one-to-one? And anytime you have a log equation where each expression is a log, you actually can make it one-to-one. And we're going to do that by using our combining or condensing skills. If you remember in the study of log rules, when you have the sum or difference of logs that have the same base, you can actually combine them into a single log. And so that's actually what we're going to do here. We are going to combine these two logs into a single log. We already have a single log over here, and then we're going to have a log equals a log, which would then satisfy the one-to-one criteria, and we can solve it that way. If you had two logs over here, we would combine these two, combine those, and still proceed. When you cannot do that, which I have an example of later, is if you have a couple of logs and you have a number by itself, we're not going to be able to combine a log with a number, and so those are the ones that we won't be able to do one-to-one, and we'll end up doing inverse property on. Okay, so let's get started on this. So if you remember using our combining skills, because these are the same logs, they both have a plus sign in front of them, which means you're going to take these arguments and combine them into a single log, and they're going to be in the numerator. If we had a negative sign here, for example, we would take this expression and put it down into the denominator of the argument, but both positive, so they both go up top. So I have combined this into a single log. This over here was already 1 log. So now that I've done that, this is now 1 to 1. So I can proceed with the 1 to 1 process, which says I'm allowed to take these arguments and just pull them out and create an algebraic equation, actually. So x times x plus 2 equals x plus 6. I can tell already, because of this x times x plus 2, if I push this through, I'm going to end up with a quadratic equation out of this. So let's get that set up. X times x is x squared, x times 2, that gives me a 2x, and I have the x plus 6. So because of this square here, definitely a quadratic. I want to set it equal to 0 and then probably utilize factoring techniques. Okay, so if I subtract this x and this 6 over here, I'm going to end up with x squared, let's see, that'll be plus x, and then minus 6 equals 0. And so if I factor this using my factoring skills, x and x, I'm going to have a 2 with a 3. The 3 will be positive and the 2 will be negative. That's how I'll get that middle term being positive. Again, if you're not sure, you can always FOIL it back together to confirm. Zero product property says take each one of these, set them equal to 0 one at a time. X minus 2 equals 0, x plus 3 equals 0. If I do that, I get these two solutions, x equals 2 and x equals negative 3. And so at this point, you might think you're finished, but remember this last thing, we have to check these answers. And what that means is if you get more than one answer, one at a time, you have to take this value for x and place it up in every spot that you see an x in the original equation, and you have to make sure that all of those arguments are still positive. So if I check x equals 2, if I put a 2 there, that's definitely positive. If I put a 2 there, that would be a positive 4, I'm fine. And if I put a 2 there, that is a positive 8. So I'm good. So x equals 2 will be a solution. Now let's move to x equals negative 3. Okay, right here, do you see when I try to put that negative 3 in, that does not work. So we are going to discard this answer. Notice if you had put the negative 3 in here, we also would have failed. Negative 3 plus 2, that ends up being a negative 1. It would have been okay over here, but the bottom line is you cannot be negative in any of those arguments. So if you fail in even one spot, you are done, and you do not get to include that as an answer. It is a domain restriction. And so x equals 2 is actually the only answer that I would include for this problem. Okay, so let's keep moving. Okay, we are going to keep moving with 2 more examples. The second example, this is definitely a log problem. We see the variable embedded inside of a log, so it's definitely a log problem. Now if we ask ourselves, is it 1 to 1? We can see that it's not. I do not have a log equals a log, and because I have these coefficient terms, I'm not going to be able to manipulate it to make it 1 to 1. So that means this problem is going to have to be done the long way, which means we're going to use the inverse property, and we're going to turn it into its exponential counterpart. Okay, so how do we do that? We are not allowed to do that until we have a single log equal to some number. So we're going to have to do some algebraic manipulation. This problem only has 1 log, so I need to start kind of peeling back the layers of the onion to get it isolated. Okay, so how about we move this 6 over? So if I add 6 to both sides, I will end up with 12 equals negative 3 times the log base 2 of 2x plus 1. Okay, so this negative 3 cannot be here either. Again, to turn this log into an exponential, I need this log piece completely isolated. If you wanted to, you could take this negative 3 and using a log rule, you could pop it up as an exponent on this argument. I don't think that's the best way to do it. I would much rather let's just divide it away, especially since 12 is divisible by negative 3. If it wasn't, I would still probably do it that way even if I ended up with a fraction. So now I have negative 4 equals the log of 2x plus 1 to the base of 2. And so this is now a single log equals a number. And so it is ready to use the inverse property on, and what I like to say, kind of backwards map it, or just map it into exponential. Okay, so if we recall how to do that, this is the argument. The reason we do this is that variable I'm trying to hunt down, I'm trying to solve for that x, I will not figure out what that variable is if it's stuck inside of a log. I need to get it out. Cannot use one-to-one property to do it, so I'll use the exponential equivalent instead, because that allows you to take that argument, which in this case is 2x plus 1, and set it equal to the base of the log becomes the base of the exponent, that 2 right there. And this number over here that was by itself, it now becomes the exponent in the exponential form. And so now that I've done that, I've got my x out of the log. And so now this becomes an algebraic simplification problem to try to isolate that x. One thing, it might not look that pleasing to the eye because we have a negative exponent here. If we remember our exponent rules, we could actually write this as the reciprocal of 1 over 2 and change that to a positive 4. And 2 to the 4th, that's actually 16. So what I really have here is 2x plus 1 equals 1/16. Okay, so again, maybe not the most attractive algebraic problem to go solve because of this fraction, but definitely manageable. So let's go ahead and move that up over here. I'll rewrite that. So we have 2x plus 1 equals 1/16. Okay, so to isolate this x, I'm going to have to subtract this 1 over, and then I'll divide by 2. So let's get that 1 subtracted first. So we have 1/16 minus 1, basically. Well, another way to write that is 16/16. You could do that in your calculator if you want to, but if you want to do it by hand, we'll need that common denominator so we can combine those fractions. So we actually have minus 15/16 if I do that math. So 2x equals minus 15/16. If I divide both sides by 2, that has the net effect of dividing by a 2 here in the denominator. So if I do that, I'm actually going to get that x equals a negative 15, and I'll have 2 times 16 down there, which is 32. So this is what I have gotten for x. The question is it allowed? I need to check that. Now, in this problem, the x was only in one location, so I need to take this negative 15/32, plug it right here, and see if this expression is positive. If it is, this will be an acceptable answer. If it's not, I will cross it off. And then if that was the case, if we cross it off, there'd be no solution because the only option was discarded. But let's see if it works. So 2 times a negative 15/32 plus 1. So the whole question is that a positive thing? Let's go ahead and get the calculator out to try to confirm that. So I have 2 times, I don't know how well you can see that on the screen, 2 times a negative 15 divided by 32, and then I'm going to add 1 to that. And when I do that, I get, it looks like 1/16, which is clearly positive. So that means if I check this answer, I get a positive value here. So it's okay. So I am good, and this is a solution to that log equation. Okay, one more. This problem illustrates quite nicely. We may still need to use combining skills even if it's not one-to-one. So this is not a log equals a log. I see this number, so that's a big clue that this is not going to be one-to-one, and I'm going to want to use inverse property. However, as I mentioned in the problem above, you're not allowed to use that inverse property until you have a single log. So if you have multiple logs and a number, you want to get the number on one side of the equal sign, and you want to get all the logs on the other. And if I combine that using my combining skills, I will write this as a single log. They're both natural logs, so I'm allowed to do this. And if I get ready to write what's going to be embedded in there, recall when you have a positive sign in front, that term will go into the numerator of the argument. When you have a negative sign, you actually have to take this argument and drop it down below. And so when we do that, we can see that this is now ready to go for the inverse property. So we are going to take the argument of the log, which is x over x plus 1, and we're going to actually write that equal to, remember this base right here, that's an e. If it's not written, putting it in might help you see how to make the transition into exponential form. So x over x plus 1 equals this base, and that becomes my power, e squared. Okay, so this is now an algebraic equation that we need to go solve for x. Now, again, it may not look that attractive, mainly because we have x in more than one location, and one of those locations happens to be a denominator. So let's brush up on some algebra skills. So first of all, I will not figure out who x is if he's stuck downstairs in the basement. So how about I get him out of there? I can do that if I multiply both sides by x plus 1. So that has the net effect of turning this into x equals e squared times x plus 1. Okay, now I still see that variable in two spots, but at least they're both up in the numerator now. And if you remember, when you have your variable in two locations, the goal is, these are both linear terms because we have x to the first. So the goal is to get all of the x's on one side and the numbers on the other. So first, let's get this e squared pushed through. So I have x equals e squared times x, and then plus e squared. At least now I can see these x terms. Okay, so I want them all on the same side of the equation. I'm going to subtract this over here. So I have x minus e squared times x equals e squared. Okay, now that these are both on the same side of the equation, I can factor this x out as a greatest common factor. If I do that, when I pull the x out of here, I have a 1. There's my minus sign, and when I pull the x out of there, I'm going to have an e squared. So this looks at least more manageable. Let me rewrite this over here. X times 1 minus e squared equals e squared. Okay, so now to isolate the x, hopefully you can see that I just need to divide both sides by this expression, 1 minus e squared. If I do that, that happens, and this is what I end up with. So e squared over 1 minus e squared. Now this is called an exact answer. The problem is I don't really have any idea what that is in terms of a number. And remember, we're going to have to go back and we're going to have to check this in our original equation to see if it's allowed. So one kind of slick trick on this one is, because I just have this x here, the bottom line is, if this number is positive, I'm going to be okay, because I'd be putting a positive thing right here and a positive thing here and adding 1. So I would be fine. But if this number is negative, it's going to fail right here. So what I really need to ask myself is this thing a positive or is it negative? That will be the crux of whether it passes or fails. And so let's do this in the calculator. And remember, you have an E button. E is just the number 2.71, and it goes on forever. It's an irrational number. So let's get this into our calculator, see what we can figure out. The E button is, the e to the power is actually above the natural log button. So let's get this typed in. So first of all, I have e squared. So I'm going to hit my shift key and get that e. So my calculator is asking me e to the what? So I want e squared, okay? And I'm going to divide that by, oops, let me get out of there. Okay, so e squared divided by, I'm going to protect this denominator with parentheses because of this negative sign here. So I want to make sure I keep this all together as a unit. So I'm going to have 1 minus, and then I need that e again, e squared. And then I can close that denominator. So that looks like what I want to have my calculator evaluate for me. So the big question is it positive or is it negative? And let's see. Okay, so according to the calculator, that is a negative 1.15. 0.565. Clearly it's negative, which means this is not going to work. So this solution would not be allowed. It's the only solution that we came up with algebraically, so that would mean that this log problem actually has no solution. So I hope that was helpful. I tried to give you some additional examples of problems that were a little bit more complex. We had to remember our combining skills. We had to use our calculator to do some checking. But hopefully having these few examples gives you a good foundation to help you work through your assigned problems.